I've never done the classic proof of E is irrational with you. What I did do many videos back was the alternating series proof. Now that's a really nice proof, and I'll leave a link to that in the description box. But the good old classic proof is very similar to the Liouviille proof for E squared is not rational. It has very similar themes and ideas. I'm not sure who was the first to do the classic proof. Some say Hermite, some say Fourier, but I'm sure it's more than one person who composed the most elegant version of this proof that we will see today. I'm going to do the classic proof first of this E is not in Q, and then apply the same ideas to E squared is not in Q. So that's the plan. Recall the power series for the exponential function. Now let's put x is equal to 1. We get this infinite series, and we can write it like that. So let's assume, like usual, we'll start by assuming E is indeed rational, and then we will draw some kind of contradiction from this. So if E is rational, I should be able to write E as m over n, where m and n are both natural numbers, like so. So the following must be true for any natural number little n. N factorial big N, E is little n factorial m. Or like this, I can write the series expression for E here. All right, so this is our starting point. This must be true for any little n, and we will show that this is impossible for all n. It will lead to a contradiction. All right, so the first thing I'm going to do is give this some names. I'll call this the left-hand side. This part here, this here is the left-hand side, and I'll call this here the right-hand side. Now you have to help me, and you have to remember what is the left-hand side and what is the right-hand side, because I will refer to them. Let's have a closer look at the left-hand side. And here I wrote my series all the way up to 1 over n factorial here, and then I continue with the tail over here like this. Okay, so I actually can write this as two pieces now. I've got the first piece, which is the sum going all the way up to the nth term, and this little n is the same n that I've chosen over here to multiply both sides. And then I've got the tail term here, the rest of it. All right, so these are two pieces, and I could call them A and B. This will be A, and this part will be B. And now it's time to examine A and B carefully. Let's look at A. We can multiply everything through by this n factorial here. What we get is this. Now this is 1, but all of these here are all integers. And so, well, this is also an integer. So this means this whole thing here, A, is a natural number. I mean, think about this. The n factorial is divisible by any of the factorials that are smaller. All right, so keep this in mind. A is for sure an integer. Now let's take a closer look at B, and what I can do here is take this little n factorial and multiply it through on every term. So I get this, and I get all this fun factorial stuff, which is a lot of fun to kind of cancel out, and you see that all of the factors that are below n plus 1 get canceled out, and I'm left with the following. Okay, that's just a straightforward division of each one of these terms here. Now, every one of these terms is positive, so what this tells me is the following. B is for sure bigger than the first term here times n. So I know this. This is our first result about B. That's very good. But I can do better than this. I can try to approximate it further by making an inequality. So let's try to construct our own home-brewed inequality from this. So what I want to do is focus on this infinite series, which is in those square brackets there. Okay, I'm going to write that out here. Great. All right, so I have this stuff that's in those brackets. I have that over here now. And I want to create something bigger than this. All right, so how am I going to do that? Well, let's see. What I can do is take each term and use each term to construct something that's greater than or equal to the term on the left. All right, so 1 over n plus 1, that's greater than or equal to this. And I can replace this n plus 2 by an n plus 1, giving me 1 over n plus 1 squared. This is bigger, strictly bigger than this here. And so on. This here, n plus 1 cubed, and so on. So n plus 1 cubed, this is strictly bigger than this. So in fact, I can take that away and say it's strictly bigger. Very good. Okay, let me get some room here. Well, this part here, this is just a geometric series. So we can easily sum that. So I have that here, and I'm going to factor out 1 over n plus 1 times like this, and so on and so on. Okay, so that's easy to sum up. I just use geometric sum formula, and you know how that goes. So that's going to be what? 1 over 1 minus 1 over n plus 1, like so. And that simplifies to this, and just a little bit more. This cancels out, and I get 1 over n. Now, if I multiply everything by big N, I get an inequality for big B here. Big B is less than big N over little n. There we go. And putting together what we have proved, we see that big B is in between these two bounds. Now, this is very interesting because what happens when n is large? Well, when n is large, when little n is bigger than big N, well, this cannot be an integer. So eventually, you can choose a value for n such that big B is not an integer. All right, so for some value of n, big B is not an integer. So what about the left-hand side? Left-hand side for some value of n is a plus b. This is an integer times something that's not an integer. Well, this is not an integer. Okay. However, what was the right-hand side? Right-hand side was little n factorial big M, but this, of course, is a natural number. It's an integer. And therefore, what do we see? Well, we see the notion of that left-hand side equals right-hand side equation. This is a contradiction. This is a contradiction, so therefore E cannot be rational. All right, so that's a very beautiful proof that E is not rational. I encourage you to go see the alternating series proof. That's also very beautiful and different from this proof. But we need these ideas. Now that we worked through this, it's much easier to get through our next job, which is Liouvile's proof about E squared. But first, a wee bit about series. This was our exponential function, and we were able to determine a series for E by plugging in x is 1. But we can also find a series for 1 over E by plugging x is minus 1. There. And we will be using this series in Liouvile's proof. Also, in the course of the calculations for Liouvile's proof, we'll run into some alternating series, and we'll need some results about alternating series. I did 2 videos on it a while back, and I'll leave the links in the description box. So here's the standard alternating series, and this series converges if and only if we have these conditions. AK is positive, and the limit of the sequence AK is 0, so it's a diminishing sequence. So it's very well behaved sequence, very well behaved series if the terms go to 0, and if they're all positive, then wham, it converges. So I proved a lot of things about this type of series in those vids, but I will need here only one of those properties. And that's this property here. The partial sums of this series are bounded above by the first term. So what does that mean? Well, the first partial sum is just a1, and that's less than or equal to a1. Second partial sum, a1 minus a2, that's bounded by a1. And then a1 minus a2 plus a3, that's going to be less than or equal to a1, and so on and so on. So this is always true for all the partial sums. That means it's also true for the limit, so it's true for the entire series. So the entire series is less than or equal to a1, like this. So here's Liouvile's clever idea. Suppose e squared really is rational, and let's see if we can get a contradiction. Okay, so no surprise here, it's a proof by contradiction. So I can assume e squared is big M over big N, with Mn are natural numbers. Okay, bring that n to the other side, and now I multiply both sides by n factorial. We saw this before, so I get this thing now. Great, so far so good. Now here's the clever idea of Liouviile. I'll take one of these e's and bring it to the other side, and I get this. This is the key idea here. Okay, so I will again call this the left-hand side, and I will call this the right-hand side. And I'm going to study the left-hand side and the right-hand side carefully. Left-hand side has to equal right-hand side for any of these n's, but in particular, it must be true for even n's. So let's assume that n is even from here on in. Let's examine the left-hand side now. I can split up my left-hand side like this, where the first part goes up to 1 over n factorial. Let's try to write that neatly. Okay, so we saw this before. This we called a, and this we called b, and we proved that this was an integer, and we proved that this is not an integer. For some values of n large enough, this is not an integer. Not an integer. And we proved this earlier, and now you see why we had to do the proof E is not in Q, because it contained many ideas that we're using now. All right, so let's look at this. B is being squeezed. Okay, as n gets large, B has to become really small. So B can become arbitrarily small. I just choose n large enough, little n large enough, and I can make B as small as I want. It has to be squeezed between these two numbers that get smaller and smaller and smaller. And so this means that, get this, this is the following beautiful idea. This is also part of the the Liouviile beautiful idea. This is an integer plus some small positive number, call it epsilon 1, where you can make that as small as we like. And so the left-hand side approaches an integer from above. There, this is a key concept, so don't you forget this. This is a beautiful idea. So we've taken the classic proof about E, and we've extracted a little bit more information. And now we see that the left-hand side is an integer plus some positive number that can be made as small as we like. A similar analysis for the right-hand side is more involved. Recall that the right-hand side is n factorial big M 1 over E, and that n is chosen to be even. Employing the usual strategy, we can split our series up. And recall that because n is even, this sign here ends up to be plus. It works out to be plus. I'm sure you can see that if you think about it for a second. As before, let's call this A. And let's call this b. The same argument like before tells us that a is an integer. There's just a little bit of worry about whether this is a positive or negative integer because we have this positive and negative signs. Well, with more alternating series theorems, we can deduce, we can show that, yeah, this is positive. But I don't think we need to know that. I think that we're okay if we just say that, yeah, it's an integer. The proof will work, I think. Now the real issue is b. Let's examine b. Okay, there's b. Now I did a couple of things. First thing I did was I factored out a minus sign, so that changed the signs here. Then the next thing I did is I took this n and I distributed, and I canceled out a whole bunch of stuff, and I am left with this alternating series here, which is in the proper canonical form for an alternating series. Now it's time to use that alternating series result that I talked about earlier, where we can set an upper bound for the alternating series. The upper bound is going to be this first term here. So okay, yeah. Let's give this series inside these brackets a name, and we can call that minus b over m, because that's what it is. I just take this minus m and bring it to the other side. Okay, so minus b over m, we know that this is bounded from above by 1 over n plus 1. And actually, this bound is strict because all these terms of the series are positive. They're not counting the signs, they're all positive numbers, and they are diminishing, and the limit is 0. So this is going to be strict, in fact. And there we go. There is our first result about b. But what else can we prove about b? Well, we can prove more things. Let's go back to that series inside the brackets, minus b over m. Now, from this, I want to construct another series that will be smaller. So for the moment, I will write smaller like this. So less than or greater than or equal to. So what I'm going to start writing here will be a smaller series. And hopefully I will get rid of that equality. Well, the first thing I can do here is write 1 over n plus 1. Now, if I compare these two, this and this, yeah, it holds. This one here is a bit greater than or equal to the one I just wrote. Now, what I can do here is I can take this term, okay, and replace this term with something bigger. Okay, well, this bigger. Okay, so I'll keep the minus, and I'll replace this with something bigger, and this is bigger, n plus 1 squared. Okay, so I'm subtracting something that's bigger, so of course what I'm building here is becoming smaller than what minus b over m is. Now here I can just change this to a negative, and right away I'm going to get something which is going to make this sum on that I'm working on here smaller than minus b over m, 1 over n plus 1 cubed. I'll choose that. Okay, and so on and so on. So I keep going with this. Minus 1 over n plus 1 power 4 would take care of the next term, and on and on and on. So all of the terms here are negative, and the ones corresponding to this, they are bigger, so I'm subtracting a number that's bigger, making this series smaller, whereas the other one, I'm just changing the sign. And so, in fact, I've built something here that's strictly smaller. It doesn't really matter if it's strictly or not strictly. I could do all of these calculations with this, but I mean, it's interesting to think about these things. So I think this is a strict inequality here, so I can leave it that way. So as an exercise, you can sum this new series that we've created that's smaller than minus b over m. So you can sum this and get an answer for this. I'll show you what that answer is, but you try doing it. It's very fun, actually. And if you do that, you get this. And from this, we can now get another inequality for B. There, we've got it. Okay, so we have enough information about B to complete Liouvile's proof. Now we're ready to put it all together. These were the two inequalities we proved about B. Let's combine them together. Yeah, now the first thing that we see here is that this is negative, so this is less than 0. And the next thing we see is that as n becomes large, B is squeezed in between these two values. The two values on the left and right of B become very small and very close together because this becomes closer and closer to 1. So B is squeezed between two negative values that both go towards 0 from the negative side. So B is a small negative number. B then can be made as small as I want. I just choose a sufficiently large n to make it all work out. And I can say B approaches, I'll put a negative in front of epsilon 2 to stress that it's a negative number. And I'll take epsilon 2 to be some really tiny positive number. Okay, so there we go. And so from this, we see that the right-hand side is an integer minus epsilon 2. All right, good. So let's think about this. The right-hand side approaches an integer from below, but the left-hand side approaches an integer from above, like this. But this is impossible. And here is your contradiction. This cannot be true. Now, that's very interesting because have you ever seen a contradiction like this before? So this contradiction is a kind of new one. This one is a little tiny bit infinitesimally larger than an integer, but this side is infinitesimally smaller than an integer, or arbitrarily smaller than an integer. So that's a contradiction. This is an unusual kind of contradiction. We haven't seen it before in my videos, at least. So this is something worth thinking about. And so then e squared cannot be a rational number. So here's an interesting question, though. We already know that e is not rational. Isn't that sufficient to conclude that e squared is not rational? Can't we just say, okay, the square of an irrational number is irrational, and that's it, we're done. Okay, so e squared is irrational. So why not? Why not? You tell me in the comments why this is a bad argument. Okay. Well, like, comment, and subscribe if you like this. Send me a super thanks. Some of this was quite hard for me to explain, and I hope that I did it in such a way that you could follow. If not, let me know, and I'll try to fix something. And I will see you next time with more really cool math stuff.